Today, we're going to practice setting the speed of a DC motor. In order to do that, we're going to use these devices, which we've used in class before in order to learn how to read a potentiometer. Today, we're mostly going to be using this part of the device, which is a DC motor. You'll notice that this part of the device has just two leads coming off of it. Find those two leads, as those are the two we'll be hooking up today. Now, let's start by attaching the device to the board. Your board might already have the device attached to it. If not, place the device so that the two mounting holes overlap two of these three holes here on your board. And take the 440 machine screws, which look like this, and pass the screw up from the bottom of the board and screw it into the device hole like this. These screws don't have to be very tight. We're just using this to keep the device in one place so that when we do future labs where we're controlling the position of the slider, it won't be moving around all the time as we try to change its position. Now, we know that we control the speed of a motor by giving it a pulse width modulated signal. Remember that a pulse width modulated signal is a signal where we turn a voltage on for a time and then off for a time and then on for a time and so forth. And remember that the amount of time that the pulse is on is known as our compare value, and that the entire time from one pulse going on until the next pulse going on is called the period. We can set the speed of the motor like this. We know that the ratio of the compare value to the period is equal to the ratio of the speed that we want, or the speed that the motor is actually going, to the value of the no load speed. So, for example, if we set the period to 100 and the compare value to 50, then the speed would be half of the no load speed. Now, recall that this only works as long as the value of the on voltage is the rated voltage of the motor. For our motors, their rated voltage is 9 volts. But the voltage that comes from our P-sock is either 3.3 volts or 5 volts, depending on how we set it. So how can we get a pulse width modulated signal where the on voltage is 9 volts? In order to do this, we need to set up a circuit. I'll move these wires out of the way here so that you can see what I'm doing. We're going to use these chips that look like this. These chips are sometimes known as motor driver chips, and they're also known as quad H-bridge chips. Basically, this chip consists of a number of individual transistors. A transistor is a kind of a digital switch where when you turn on the voltage to one pin, the voltage is allowed to travel freely between the other two pins. We're going to use this device to allow us to use the voltage from the P-sock to turn on and off an external voltage, which we will plug in to this barrel connector here. If your chip isn't already attached to the board, carefully line up the pins with the holes in the board, and you're going to want to press it in. Here's a page from the datasheet for this chip showing how the chip works. First of all, we need to give power from the PSOC to pin number 1. This EN stands for enable. So the chip won't work unless we have power to pin number 1. Secondly, the VCC pin is the pin that receives the higher voltage that we don't want to go through the PSOC. This is the pin to which we will connect power from the external power supply. Pins 4 and 5 are connected together and they're both connected to ground. We need to make sure that either pin 4 or pin 5 is connected to ground of the external power supply and also ground of the PSOC. We always need to make sure that all of our grounds are connected together from the PSOC, from the power supply, and the chip. Now here's how the A and Y pins work. We want to connect 1A and 2A to PWM pins on our PSOC. When we set pin 1A high, the voltage attached to VCC2 will be allowed to flow through pin 3. So if we attach one of the motor leads to pin 3, then every time we turn on pin 2 with the PSOC, the higher voltage will be allowed to be applied from pin 8 to pin 3. It works the same way down here. If we connect our PWM pin from the PSOC to pin 7, every time that voltage goes high, the high voltage from our external power supply will be allowed to go out pin 6 or 2Y. We also need to put a jumper wire between pins 1 and pin 16 in order to enable the chip. Now notice that this chip has an identifying mark to let you know which direction is the top of the chip. If you look at your physical chip, I'll show you a picture here. If you look closely at your physical chip, you will see that there's a small indentation at the top of the chip. That indentation indicates which direction is up. So you have to make sure that you identify which direction is up so you know which pin is 1 and which pin is 8. Now let's go back to our board and connect this circuit. I'm going to start by setting up power and ground. So I'm going to take power from the power supply and I'm going to connect it to pin 8. Then I'm going to take ground from the power supply and connect it to pin 4. So that's all I need to do to set up my external power. Next, let's connect the PSOC. The first thing I'm going to do is set up ground of the PSOC. I'm going to turn the PSOC over and find a ground pin. There's a ground pin. And I'll connect ground to either pin 4 or pin 5 of the chip. Next, I'm going to find a VDD pin on the PSOC. There's a VDD pin right there. And that needs to go to pin 1. Now note that this is only going to work if your PSOC is set to run on 5 volts. So look at your little jumper up here and make sure that you've set the jumper, connected it so that it's connected to 5 volts and not 3.3 volts. Now we need to connect together pin 1 and pin 16, the top pin on the other side of the chip. Next, I'm going to take 2 pins on the P-sock that we can use for our PWM outputs. I'm going to use pins 1, 1 and 1, 2, which are right over here. Pins 1, 1 and 1, 2. One of these has to be connected to pin 2. I'm going to connect pin 1, 1 to pin 2 of the chip, and I'm going to connect pin 1, 2 of the P-sock to pin 7 of the chip. And now let's connect the motor. I'm going to take one of the 2 motor leads, right now it doesn't matter which one, and connect it to pin 3 of the chip. And I'm going to take the other motor lead and connect it to pin 6 of the chip. Don't plug in your external power supply yet. First, let's write some code for the P-sock. So I haven't plugged in my P-sock yet. I'm going to go ahead and do that before we move on. Open up P-sock Creator and create a new project. Now we're going to find the PWM block. Go to Digital and then Functions and find PWM TC-PWM mode. Now this may be surprising right now, but we actually need to have 2 of these PWMs. And in a moment I'll show you why that is. Go down to System and find a clock and wire 1 clock to each of these PWMs. You can't use the same clock for both of them, unfortunately, so make sure you have 2 different clocks. Then go to Ports and Pins and place 1 digital output pin on the line output of each of these blocks. Alright, now let's go set our pins. We'll come back here in a moment to set the settings of the PWM. We want to set these pins to the 2 pins we plugged into the motor driver chip for controlling the motor. Remember, we connected those to pins 1, 1 and 1, 2. Now go back to the top design and double click on your first PWM. In the PWM tab, first of all, leave the prescaler set to 1x. You might remember that when we were driving the servo, we set the prescaler to 4x. We did that because the timing to set the positions of the servos was very precise. It had to be exactly what the servo required. Here, we'd like it to be as fast as possible, because the faster the timer is, the more the speed of the motor will be smooth instead of jerky. If we had a very slow clock running our PWMs, instead of going at, say, half the speed, if we set the compare value to be half the period, the motor would just go full on and then full off half the time. So we want the timer to be as fast as possible for motor control. Now set the period to be 100 and the compare value to be 0. We want to set the period to 100 so that it's easy for us to understand what speed we're commanding to the motor. If the period is 100, then whatever number we write to the compare value is a percentage of full speed. In other words, if we set the compare to 100, we would be commanding the motor to move at 100% of its full speed. If we would set the compare value to 50, we would be commanding the motor to move at 50% of its full speed. That's why we've chosen 100 for the period. Click OK, and then do the same to your second PWM. Now let's go write some code. Double click on main.c. We'll delete the comments, and we also don't need global interrupts here. The first thing we need to do is to enable those two PWMs. Now, here's why we placed two PWMs. The first PWM will be controlling the amount of voltage we give to one of the motor leads, and the other PWM will control the amount of voltage we give to the other motor lead. So, let's do a test where we make the motor move forwards and backwards. The first thing we need to do is set the compare value for PWM1 to 100. Now, at the same time that we do that, we need to make sure that we set the compare value for PWM2 to be 0. That's because we don't want to give voltage to the two leads of the motor at the same time. In order to make the motor move in one direction, one of the leads has to be pulled to ground while the other lead is activated. Now, let's put in a short delay. Then, let's make the motor move in the other direction. To move in the other direction, we have to set PWM2 to 100, while we set PWM1 to 0. And then delay. Go ahead and build your code and program the PSOC. Once your PSOC is programmed, you want to plug in the external power. Once you've gotten the device moving back and forth at its full speed, let's see if we can figure out what is the no-load speed of this device. Right now, it would be hard to figure that out because the device is moving so fast for a long enough amount of time that it hits both ends of the slider every time. We want to change our code a little bit so that we can measure the distance that the slider moves every time it goes back and forth. If we can measure that distance and we know how much of a delay is being used, we can calculate the speed by taking the distance divided by the time. Let's try it. Right now, the code that we've written is doing the following. It first turns the motor on at 100%. And this is going in the forwards direction. Then we leave the motor on for 500 milliseconds. Then we turn the motor on backwards at 100% speed. And we leave the motor on going backwards for 500 milliseconds. In order to measure the no-load speed of our motor, we want to turn the motor on forwards at 100% speed. Then leave the motor on for a short enough amount of time that it will not hit the other wall. I don't right now know how long that is, so we're just going to guess for now. Let's try 100 milliseconds. Then the next thing we want to do is turn the motor off. The way we turn the motor off is by setting a compare value of 0 to both of the PWMs at the same time. Next, I want to leave the motor off for a good long amount of time so that I can note its position. Let's give ourselves 5 seconds. Next, I want to turn the motor on backwards at 100% speed, but then I want to leave it on backwards for a short amount of time again, say 100 milliseconds. Lastly, I want to turn the motor off and then leave it off for a long time again. Build your code and program the PSOC. After your program has finished downloading to the PSOC, plug in the power and watch what happens. It's doing the correct weighting that we wanted it to do, but it's still going all the way across the slider every time. We need to make our delay a shorter amount of time. Back here in the code, let's make the delay half of what we set previously. Let's make it 50 and 50. Now, the slider hits only one side. Let's try and get the slider so that it moves both directions, not hitting the end of the slider. Perfect. When you get your slider so that it moves and does not hit either side, wait until it stops at a position and mark that position on your board. Then, when it stops in the new position, mark that position on the board. Now, take a ruler. Use your ruler to measure the distance between the two marks that you made. Here, mine is about 6 centimeters. We now have everything we need to know in order to calculate the no-load speed. Back in our code, let's put in a variable to calculate it. I'm going to create a floating point variable called no-load. The no-load speed, which is in a speed unit, centimeters per second, will be equal to 6 centimeters, and that those 6 centimeters are traveled during 50 milliseconds. Now that we have the no-load speed and the compare value, we could specify a target speed and then use our equation to calculate the correct compare value to move at the target speed. Let's try that. I'm going to create a new floating point variable called speed, which we can set ourselves in units of centimeters per second. Now we know that the no-load speed, that is the fastest speed the motor can move, is equal to 6 divided by 0.05. So the fastest the motor can move is 120 centimeters per second. We want to make sure that we don't command a speed faster than this. Let's try 100 to start out with. Now let's create a new variable that is an integer. We'll call it the compare value. Here we're going to use our equation that we learned earlier. This equation says that the compare value divided by the period is equal to the speed divided by the no load speed. So if I want to solve for the compare value, I could take the speed divided by the no load speed and multiply that by the period, which is 100. Then, down here, instead of commanding 100 as the compare value, we're going to command the value of the variable we created called compare. Now before we run this, let's think about what it is we expect to see when we run the code. Our target speed is 100 centimeters per second, and right now we have a delay of 50 milliseconds. So how far would we expect the slider to slide? We can take our speed, 100 centimeters per second, and multiply that by the number of seconds in our delay. 50 milliseconds is 0.05 seconds. That gives us 5 centimeters. When we run this code, we would expect the slider to slide 5 centimeters each time. Let's check and see if this is correct. Go ahead and program the PSOC. We're going to erase the marks we had last time so I don't get confused, and then plug in the power. I'll make a mark at one end of the slide and another mark at the other end of the slide, and then measure the distance between them. You'll see that the distance of the slide falls short of what I would expect. It really only goes about 4 centimeters. The primary reason for this has to do with the amount of torque required for the motor to move at all. Inside the motor, there's some amount of friction that has to be overcome before the motor will move at all. Let me show you an example of how that affects our motor motion. I'm going to take the delay between moves and reduce it to only 1 second so that we can see this motion more quickly. Then, in place of the compare value, I'm going to type in 50. We would expect this to move the motor at half speed. Try and program the PSOC and see what happens to the motion of the motor. You will notice that the motor hardly moves at all. This is because this motor and slider has quite a lot of friction impeding the motion. Almost 50% of the voltage is required just to get the slider to move. In motor terminology, this is often referred to as stiction, which is the two words static and friction stuck together. Motors all have some amount of static friction that will throw off your calculations of motor speed. You have to be aware of that when you're doing motor speed control. Do a few more experiments to figure out what is the smallest compare value you can give to your motor before it will not move at all. Record that number because you'll need that in later parts of this lab.